right, as we get started, I want to quickly review a couple of pictures here. I told you you're going to have a quiz in this lesson here in just a moment, but it's going to involve really just these two pictures. Theorem 53, we said that if you have a triangle in which one line divides two sides and is parallel to the third side, then this line will divide these two sides proportionally, so that three different proportions could be formed. Kendall, can you give me one of the proportions in words, first of all?
Bottom is to top as bottom is to top.
Good. Bottom is to top as bottom is to top. Now, in letters, what would that look like, Kendall?
WZ is to ZY.
Good. This bottom segment, WZ, is to its top segment, ZY, as?
XG is to GY.
There we go. As this bottom segment is to its top segment. Another proportion in words, Audrey.
Whole is to top as whole is to top.
Whole is to top. What would that look like, Audrey?
WY is to ZY as XY is to GY.
There we go. And then the final proportion, Ethan?
Whole is bottom, whole is bottom.
And what would that look like in letters? Whole is to bottom as whole is to bottom.
WY is to WZ as XY is to XD.
There we go. And of course, any of these could have the inversion transformation applied to them, but this is the way we'd want to memorize it. Now, I did say this. What if I didn't know that the line was parallel? What if the question asked, is ZG parallel to WX? Then, Chris, I would have to figure out...
if it's parallel.
Yeah, in order to figure out if it's parallel, I would have to figure out... Jamie?
If the product of the means equals product of the extremes.
In other words, if I have a proportion, right? Because in order for product of means equal, we have to have a true proportion. And so there's three different proportions that if any one of those three proportions were true, then it would have to be parallel. So Chris, what's one of the three proportions that, if true, would make ZG parallel?
Whole is to top as whole is to top.
Yeah, whole is to top as whole is to top. Or perhaps, Kendall?
Whole is to bottom as whole is to bottom.
Perhaps whole is to bottom as whole is to bottom. Or Jamie, perhaps?
What is it? Bottom is to top as bottom is to
Bottom is to top as bottom is to top. If any of those three proportions are true, then it would have to be parallel. So if you know it's parallel, you know the proportion has to be true. We proved that. We also proved that if the proportions are true, then the line has to be parallel. So a converse there. Then with this picture, we had a series of parallel lines. You know, just to be interesting, I could add one more parallel through here and call this one, I don't know, T and U, for instance. Pretend it's parallel. I know it doesn't look very parallel, but we'll pretend it's parallel. We don't trust our eyes in this class. At what series of equal ratios must be true if a bunch of parallel lines are cut by a couple of transversals? Ethan?
Yeah, that's why I don't remember this.
Jog his memory here. Chris, you got this one?
I think so.
Okay.
RM
R
is to M.
is to M, right? These two form a ratio.
Okay. As Q is to S.
As Q is to S, keep going, Ethan.
V is to E.
As V is to E.
As T is to U.
As T is to U. Right. Each segment of one transversal is in ratio to the corresponding segment of the other, as any other is to its corresponding segment, as any other is to its corresponding segment, and so on and so forth. Okay? Any questions on these pictures? Clear your desk, then, except for a clean sheet of paper, a pencil, and an optional calculator. You don't have to have a calculator to complete the quiz, but it's not a bad idea, particularly if your math skills aren't particularly, shall we say, phenomenal. Sheet of paper, pencil, optional calculator. First and last name at the top of your paper, along with today's date. First and last name at the top of your paper, along with today's date, which is 3/8/21. 3/8/21.
Which quiz is this?
This is quiz 33A. Quiz 33A.
It's a B.
Which means there's a B coming, yeah.
That's
all right. All right. Pretty straightforward quiz. Numbers 1 through 4 all deal with that first picture. I've given you 3 lengths. I want you to find me a fourth length. For numbers 5, 6, and 7, I've given you 4 lengths. Yes or no, is DE going to be parallel to AB? And then for number 8 and number 9, number 8, I've given you 3 lengths, I need 1. Number 9, I've given you 4 lengths, I need 2. And there's a bonus for you as well. All right, go ahead and get started on that. Do not write on my quiz copy, no. If you need to, I would highly recommend making a sketch on your own paper and labeling on that. But no, please do not write on the quiz copy. more minutes to be finishing up. It's going to take about another minute or so. Take about another minute to finish up those last problems there. I'm going to collect those from you. Got it?
I didn't. I was missing one part of the last.
All right. Go take your homework out, if you would, please. I want to take your homework out, if you would, please. And turn to page 201. Page 201. So on Friday in our last lesson, I introduced to you a couple of pictures that we put on the pictures and proportions page, which obviously were not on this quiz, but y'all noticed the 33A. That means upcoming is a 33B. Anyone want to guess what's going to be on 33B?
Yes.
These pictures. Yeah, so let's take a look at these pictures. And I started by introducing this idea that whenever you divide a line at any point, the segments of the line are from one end of the line to the division point, and from the other end of the line to the division point. So these would be the two segments. That would be dividing a line internally. I also, though, pointed out that you could divide a line externally. Out here, for instance, as long as it was in that same line extended. So that the two segments would be from here to here, and from here to here. It still goes from endpoint to division point, endpoint to division point. And after pointing that out, I showed you that if you were to take some triangle, and you were to bisect one angle of the triangle, then this opposite side across from the bisected angle would be divided into 1, 2 segments. And the ratio these segments make with each other is the same ratio as the two sides make with each other, so that in words we would have the proportion segment is to segment as side is to side. Say that with me, class. Segment is to segment as side is to side. The same thing would be true, by the way, if we happened to have an exterior angle that was bisected. This ratio would still be segment is to segment as side is to side. Same proportion, same words. The two segments just look weird, but you have to remember it goes from endpoint to division point. That's one segment. Endpoint to division point, just happens to be out here, is the other segment. That's what we were practicing with on the homework. Page 201, you had numbers 1, 2, 4, 5, and 6. All right, 1, 2, 4, 5, and 6. All right, the problem was you didn't draw any pictures. You can't hope to figure it out if you don't draw a picture. Come on, do better than that. You did not attempt them. You're technically not required to, though it would have helped you a lot, I think, if you had, but you weren't required to since you were not here. All right, so let's go and take a look here. And it starts by saying in Theorem 55. So, let's look across the page at Theorem 55, and here's the picture. We've got a side RS, we've got a vertex angle T, and we've got a bisector TM. Now, obviously, my picture doesn't look just like theirs, but the labeling's still all there. So in this picture, triangle RST with a bisector TM, it says that RM is 6, MS is 8, and RT is 10, and we are finding TS. In words, what proportion goes with this picture, Chris?
6.
In words, what proportion goes with this picture?
Segment is to segment, as side is to side.
Good, okay, so then in letters, what proportion goes with this picture?
RM is to MS as RT is to TS.
Perfect. Now, plugging in values, what proportion do I have here?
6 is to 8 as 10 is to X.
Good, and we can just call the missing side X. And so we cross multiply, and we solve. And 6x equals 80. Class, we end up getting x is equal to 13. I hate decimals, make a fraction. 13 and a third. And there were no units given, right? I don't see any inches or anything, so we'll just leave it unitless, 13 and a third. How many had that? For number 1. All right, question. Does that make sense now?
I know what I did. So I actually didn't know, like, I saw that it said in Theorem 55, I thought it meant, like, something in that was what we had to do. I didn't know that it gave a picture. Gotcha.
Now, we've seen this several times this year where it said in this, and we've always referred back to the picture. So, kind of, again, because otherwise you're like,
I didn't have pictures.
What's RM? Yeah. What RM? I don't see an RM anywhere.
So I actually
RM, right there.
I tried to figure out what R equaled, and then I tried to figure out what all the individual ones.
Yeah, well, again, a capital letter is a point, so 2 capital letters together refers to a line segment. So that's what we should have done there. Number 2, same picture, same proportion, different given information. What were we given this time, Kendall?
RS equals 5.
Now that's this entire side, isn't it?
RT equals 6. TS equals 9.
And we have to find both.
RM and NS.
Now this is where it's going to get a little bit sticky. I don't know RM, so class, I have to just call it X. But I also don't know MS.
X.
And MS has to go in the proportion, right? It's segment RM is to segment SM as side RT is to side ST, right? I can't plug in 12. RS ain't up here. How in the world will I algebraically represent MS if I know the whole line is 12 and this piece is X of those 12 units? Anyone?
Would it be X plus 12?
So you see, if I take this piece and I add them together, I'll get that piece?
No. It would be X. Can we make MS like Y or something?
Nope. Because then we'd have to have 2 equations, and I don't want 2 equations.
12 minus X?
12 minus X. The entire length minus however big the piece X is leaves us with 12 minus X. Does that make sense now? Algebraically representing, just like we would have done, class, in the past. If I had an arc, a circle, and I had a semicircle, and I knew that this arc was X, I would have said this is 180 minus X, right? Same idea. Just like we do with arcs and angles at times, where we had to algebraically represent things, we're going to do that here. So, given segment to segment, to side to side, Kendall, how should I plug in the numbers and letters here?
X is to 12 minus X, as 6 is to 9.
Does that make sense now? At your seats, solve. This is where the algebra begins to tie back in. In a big way, in fact. Ick.
4 4/5.
Yeah, 4 and 12/15, that would be 4 and 4/5, wouldn't it? All right, so that's RM. That's only half of what I was solving for. Now plugging that into the calculator, what is MS, class?
7 1/5.
7 and 1/5. Again, calculators help to make it easier, though I'm showing it here on the board. You can do it without, but much easier. Notice both answers to this one. Assuming nobody got it, because none of you had identified the 12 minus x, does it make sense now, though? Any questions at all? All right, let's take a look at number 4. And it gives us 4 lengths this time. And the question is, does TM bisect angle T? Well, kind of like before, if the third side is divided proportionally so that segment is to segment, side is to side, then yes, it would bisect. So we don't know it bisects here. The question is that a bisected angle? So it tells us that RM is 3, tells us MS is 4, tells us RT is 7 and 1/5, and TS is 9 and 2/5. What proportion would have to be true for that angle to be bisected, Ethan?
3 is to 4 minus 7 and 9
And this is where you just get your calculator out. There's 2 ways to do it. Method number 1 is to cross multiply. 4 times 7 and 1/5. What is that?
and 4/5.
28 and 4/5. Okay, then 3 times 9 and 2/5.
28 and 1/5.
28 and 1/5. Oh, so are they equal? No. Now it's very, very close. Is the angle bisected? Very, very close, but no, it is not bisected. The other way you could do it is you could, no, I don't think you could enter a complex fraction on most calculators. If you have a fancier calculator, you do 7 and 1/5 fraction 9 and 2/5 and see if it comes out reduced to 3/4. The cross multiplication method works
Can't
great
do that on
here.
this one?
Not on my calculator because it can't enter complex fractions, so no. No. You could make decimals like 7.2 fraction 9.4, but that might confuse the bejeebers out of it. Just cross multiply. Questions on that? Let's take a look at number 5. And here it says in Theorem 56. Oh, Theorem 56. So we got to look at the Theorem 56 picture. And here we've got a triangle RST. And once again, we've got this division point out here, M, where TM bisects the exterior angle T. All right, so in words, what proportion goes with this picture, Audrey? No, in words. Good. Segment is to segment, to side is to side. Now, Audrey, the 3 sides of the triangle are RS, RT, and TS. These are the 3 sides. One side has been divided into segments. Which side has been chopped up into parts? No, which side has been divided into parts? No, MS is not a side. Of these 3 sides, which side has been divided into parts? RS. Now, it wasn't divided internally. So again, as you're looking at it, if I asked Chloe, she'd be like, it's not divided at all, Daddy. Because it's not the way our brains naturally think. But RS has been chopped up into pieces. What are the 2 pieces of RS that have been formed?
MR and MS.
Good. MR and MS. From this division point, make the 2 pieces, MR and MS. So when we say segments to segment, Audrey, that means
MR and MS.
as...
ST is to...
Well, okay, so if we go, this segment starts from R to M. then we need the side that goes from R to T, right? So the R vertex is going to have segment in the antecedent and side in the antecedent. Does that make sense? So then segment, which has the S, is also going to have the side, which has the S. ST. Does that make sense as well? Again, it's a little harder to see with this picture. Do we see it? RM is the first segment, RT is the first side. Then MS is the second segment, ST is that second side. So another way I've described it, class, endpoint, point of division, over endpoint, point of division, first endpoint, top vertex, other endpoint, top vertex. So it kind of stays in that order. So this is the proportion we're looking at. They tell us that RS is 12. They tell us that RT is 6. They tell us that TS is 9. And they tell us to find RM. Now the problem is, class, RS isn't in here. Its RM is to MS. But, class, if RM is X and RS is 12, class, what is MS going to be?
12 minus X plus 12.
X plus 12. We see the two pieces added together would equal the whole, right? The whole equals the sum of all its parts. So X plus 12. Notice algebraic representation having to be used. This is why we teach this after algebra, instead of at the same time. So X plus 12. So, plugging these values into the proportion now, Jamie, what would it look like?
It would be X is to X plus 12 as 9 is to 12. Wait.
Careful.
Oh,
This segment over this segment, this side over that side.
6 is to 9.
6 is to 9. Does that make sense? How many had this? Anyone have this proportion?
Almost.
I didn't think so. Solve it now. And did we get 24? Any questions? All right, let's go on to number 6, our last homework problem. Same picture, so the proportion doesn't change. They just change some of the given information here. All right, once again, in words, what proportion goes with the picture, Chris?
Segment to segment to side to side.
What are the two segments?
MR and RS.
I'm sorry, MR and...
RS.
Ooh,
Oh,
RS
no,
is it? MS, there we go. RS is the actual side. RM and MS are your two segments, and the two sides.
MT and TS.
Well, MT, okay, the triangle's right here.
RT.
RT.
I have a
NTS.
brain problem.
And again, this is just such a hard one to visualize, isn't it? That's why I drill extra hard. I'm not trying to make fun of you. I'm trying to force you in the, okay, if I can think of it now when I'm being called on in front of the class, maybe on the quiz or test I have a chance, right? Because it's just hard to visualize this. They tell us on number 6 that MR is 9. They tell us that RT is 4 4/5. Aren't you glad you have a calculator? They tell us that TS is 12 4/5, and they ask for RS. Now, here's the thing. RS ain't one of these things. It's RM, which I know is 9, and MS, which I should represent, class.
X plus 9.
X plus 9. That's your C's to solve. Assuming you didn't already do this. I'm gonna get out my calculator. I ain't doing that. Within reason, but
I don't think I did it right. Yeah, I know.
well, fix it if you messed it up.
I'm trying to see what I did.
Huh. Well, compare my work to your work.
That's what I'm doing.
Alright, Jamie, good to go? Kendall, good to go? Really thankful for calculator right about now.
9 and times 12 and 4/5.
Right.
115.
And 1/5.
Yeah.
You got it.
And you're going to distribute the 4 and
right,
4/5. So
right.
4 and 4/5 x, and then 4 and 4/5 times 9 is
I
43.
turned 4 and 4/5 into a decimal.
Don't go decimals.
I hate fractions, so I'd rather.
Yeah, but how good are you at actually turning fractions into decimals? Unless you're 100%, I wouldn't mess with it. I'd stay with the fraction. Now, I know 4.8 and 12.8, but I'm really good with decimals. If you're not, I'd be very leery of it, just as a warning. Questions on this? Now, the other thing that made these last couple ones extra hard too was at the end of the hour, we didn't have time to actually practice these. So, this was literally the first time you practiced them, was on the homework, had some struggles, it already looks weird. Let's do a little bit more practice since we didn't have a chance to do some in our last lesson. Go and draw an obtuse triangle. It's a little easier to do with obtuse triangles. Again, I mentioned in the last lesson, you can do this theorem just fine without. In fact, the book shows an example of one without, but it's easier with. And to go and extend the vertex up through C, and then to the best of your ability, try to figure about where the bisector would go here, and then allow that to come out here and meet at a point which we'll call X. So we are bisecting exterior angle C with the bisector CX. Again, what would be given to you on a quiz or test is that CX bisects exterior angle C. And anytime you see a bisector of any angle, we know we're thinking what proportion class? Segment is to segment, a side is to side. Now, an exterior angle bisector does make the problem look weird, but it doesn't change the proportion in words. All right, so if I know that AX is 10, BX is 15, AC, I don't know AC, but I do know BC is 9. At your seats. By the way, I didn't specify class. How big is AB?
X plus X minus 10.
Don't overcomplicate this. How big is AB? It's
5.
5, right? The whole big thing is 15.
Yeah.
Now, I don't need that, right? But if I'd given you 5, you should have been able to get 15, right? Or if I'd given you the 5 and the 15, you should have been able to get the 10. So be able to work with those numbers. How do I plug the numbers into my proportion, Ethan?
10 is to 15. As X is to 9.
Good. Segment 10 is to segment 15, as side X is to side 9. You cross multiply, and you get X equals class?
6.
6. So I know I get 6 units for side AC. How many had 6 for this one? Question.
I didn't do 15, I did 5.
Okay, remember, segment is to segment. AB is the actual side itself, divided into segments of 10 and 15. All right, let's change it up a little bit here. Same picture, but this time I don't know AX, but I do know that AB is 8. I know that AC is 4. I know that BC is 10. At your seats, find AX. Again, given that CX bisects the exterior angle C. Audrey, in words, what's the proportion? Good. Segment is to segment, side is to side. Now, in letters, what is that proportion? Ethan?
X is to X plus 8.
X is to X.
X plus 8.
Oh, you mean XA is to In letters, like
Oh,
A, B, C,
oh,
X.
oh,
In
oh.
letters, what's my proportion?
I'd say XA is to XB as AC is to BC.
There we go. AX is to BX as AC is to BC. Now plugging that in, since I don't know AX class, let's just call it X. Since I don't know XB, but I've already chosen X to be AX, how should I represent BX class? You're going to add the two pieces together this time, X plus 8, as 4 is to 10. We cross multiply, and we get, oh, it's not going to work out evenly. We get 5 1/3, and again, no units, so we'll just say 5 1/3 is our length for AX. How many had 5 1/3? If I'd asked for BX, what would that be, anybody?
13 1/3.
13 1/3. You add 5 1/3 plus 8 to get 13 1/3. You're going to practice with more of that in your homework this evening. For now, next section in your notes. Terms definitions. Let's go back to the terms definitions section. And we're going to continue to apply proportions to geometry. Next term I want you to write down in your notes is the term similar polygons. But similar, the symbol is a squiggle. So similar or squiggle pegons. Similar or squiggle pegons. That's in fact the same squiggle that goes on top of the equal sign to make the congruent symbol, right? It's a squiggle and then an equal sign below it. That symbol means similar. Similar polygons. Polygons which have the same shape, but not necessarily the same size. Polygons which have the same shape, but not necessarily the same size. Technically, they could be the same size, as long as the shape is the same. The size does not have to be. Now, you'll remember congruency means same shape, same size. In fact, if this means same shape, and equal means same size, same shape and size would be congruent. Well, here we take the same size element off and we just say same shape. Does that make sense? Now, there's two key elements for polygons to be similar. First of all, corresponding angles must be equal. Corresponding angles must be equal. So, for instance, if I've got some goofy looking polygon here, and I've got some goofy looking polygon here. If this angle and this angle are equal, and these two angles are equal, and these two angles are equal, and this angle equals this one, and these two are equal, then we're halfway home to saying that those are similar polygons, if all the corresponding angles are equal. That's just like congruency. What doesn't have to be the same is corresponding sides won't be equal, but rather corresponding sides must be proportional. Corresponding sides must be proportional. What does that mean for sides to be proportional? Well, if I knew that this side, for instance, was 10 inches, and I knew that this was 5, the ratio here is a 2-to-1 ratio, correct? And if I knew that this side was 14 and this side was 7, well, that's also a 2-to-1 ratio. We could say, class, that 10 is to 5 as 14 is to 7, equal ratios, right? Or if this side was, let's just say 16 and this side was 8, and this side was 8 and this side was 4, and this side was 10 and this side was 5, well, in that case, it's always a 2-to-1, 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 2-to-1. The ratio stays constant. That means sides are proportional. Now, both requirements are met. If those things are true, those are similar polygons to each other. Now, if one of the sides was a little bit off, it wouldn't be proportional, not similar. But if corresponding angles are equal and corresponding sides are proportional, then we have what are called similar polygons. I want you to write this term down in your notes next, because this ratio was always 2-to-1, 2-to-1, 2-to-1. We call that the ratio of similitude. The ratio of similitude. It's a fancier word than similarity. It's a ratio that shows how they are similar. The ratio of similitude, which is a noun form of similar. Ratio of similitude. This is the ratio between any two corresponding sides of similar polygons. This is a ratio of any two corresponding sides of similar polygons. The ratio of any two corresponding sides of similar polygons. It's called the ratio of similitude. So if I, for instance, knew that this rectangle was similar to this rectangle, and I knew that this side was 3 inches and this side was 5 inches, and I knew that this side was 5 inches, and I wanted to know how big that side was, for instance. Well, if I know they're similar, then I know corresponding angles, first of all, class, have to be
Equal.
which, if they're rectangles, of course, the corresponding angles are equal because everything's a right angle. Corresponding sides have to be proportional. So that 3 is to 5, notice the inches cancel, as 5 is to x. This ratio of any two corresponding sides is called, class, the ratio of similitude. And we just cross multiply and solve to get x is equal to
8 and 1/3.
8 1/3. So apparently this would have to be an 8 1/3 inch side for them to, if they were similar to each other. Does that make sense? Questions on that? All right, we're going to talk more about similar polygons in our lesson tomorrow. For tonight, however, you're going to do handout 7. Handout 7. If you go back to lesson 86, that the very first, I think it is lesson 86, I have the geometry handout in a link in the description. Okay, but we haven't done a handout in a while. This is handout 7. Handout 7 from that list of second semester handouts. Tell you what, I'll go ahead and repost that link though, since it's been so long. That way we don't have to run the risk. Hold on, Chris. Run the risk of you not finding it. So I'll go ahead and repost the link there. But handout 7 gives you a good review over some of these pictures and proportions we've worked on. We'll talk more about similar polygons in our next lesson. Have a wonderful rest of your day.